This is the second lecture in our three-lecture theme that describes the geometry and expansion history of the universe. Last lecture, we learned that Einstein's theory of gravity, applied to a homogeneous universe, suggests its space should be either positively or negatively curved, so giant billion light-year triangles need not have angles that added up to 180 degrees. After decades of failure, the universe's true curvature was finally measured at the close of the 20th century, using sound waves visible on the microwave background. The answer? It has zero curvature to within 1% accuracy. Its space is Euclidean. Giant triangles do have angles that add up to 180 degrees. We also learned that Einstein's theory suggests this space could be expanding or contracting, and because the expansion is the same everywhere, it should obey a Hubble law. More distant regions should separate from each other proportionately faster. But so far we've said nothing about how the expansion proceeds, how it changes over time, and that's the topic for this lecture and the next. We're ultimately aiming to understand the origin of these classic expansion diagrams, S of t. Time, t, goes along the bottom, and size, or scale factor, s, goes upwards, starting at 0 at the Big Bang and 1 today. In this example, the universe expands rapidly at first, but quickly slows down, then it coasts for a while, then it speeds up. Now, the primary reason cosmologists want to know the expansion history, S of t, is because it reveals what the universe is made of, and most importantly, it can unmask the presence of dark energy, because dark energy causes the expansion to speed up. Now, our approach to understanding the shape of S of t is to start out with a simple toy model universe and apply Newton's gravity, not Einstein's, to figure out how it expands. Once we think we've understood that, we'll gently go back to Einstein's gravity and the real universe and see what needs to be modified. And surprisingly, it turns out Newton's gravity does just fine in this context, and we hardly need to change anything at all. So here's our toy model. Way out, far from anywhere, imagine we have a sphere containing rocks uniformly spread about. Let's also carefully arrange for these rocks to be moving away from the centre with a speed that is proportional to their distance from the centre, like these little arrows. Now, if I replaced each rock with a galaxy, we'd have a situation that is identical to a sphere sliced out of today's universe. It's a uniform region expanding with a Hubble law. The only difference is that the rest of the universe outside the sphere is missing, and in its place we have empty space. So here's what we're going to do. We're going to follow the sphere's expansion by following the trajectory of the outermost rock using Newton's law of gravity. Overall, I think you can sense what will happen. The gravity of all the rocks pulls backwards, so the outermost rock will move out but slow down. So let's first look at the gravitational force around this sphere. It turns out it's exactly the same as if all the rocks were at the centre, and it has the famous inverse square law, decreasing in strength with distance. Here are the forces shown as arrows. They point backwards and quickly get weaker. At double the starting distance, the backward force is a quarter as strong. At triple the distance, it's a ninth as strong, and so on. Now, because the force drops off so rapidly, you can intuit something important. If our rock slows enough to halt, it feels the backward force and falls back down. But if it gets up high and is still moving fast, the force is then so weak it won't be able to halt the rock, which will carry on and escape the system. Now, it also turns out that what's true for the outermost rock is true for all of the rocks. So the entire set goes out and either recollapses or continues forever. Which situation occurs depends on how the initial outward speed compares to the backward strength of gravity. Okay, now we have this intuitive feel for the expansion. Let's get a bit more precise. And to do this, I'm not going to focus on forces, which are easy to intuit but hard to analyse, but instead I'm going to focus on energies, which really get to the heart of what's happening. Now, it's important to realise that the outermost rock has two kinds of energy. The first is its kinetic energy. It's energy of motion. If it hit you, this energy would hurt you. In math terms, kinetic energy, Ke, is given by a half mv squared, where little m is the rock's mass and v is the rock's velocity or speed. Obviously, as the rock goes up, its speed drops, and so the rock is clearly losing its kinetic energy. So where does that energy go? Well, it's being used up as the rock moves against the backward gravitational force, just as you would get tired burning up calories if you ran up a hill. But where exactly does the energy go? It goes into the gravitational field that exists between the rock and all the other rocks. In math terms, the gravitational energy, Ge, is minus G big M little m over R, where big M is the mass of all the other rocks pulling back, and R is the distance of our rock to the centre of the sphere. And of course, big G is Newton's gravitational constant. Now, it is very important to notice that the gravitational energy is negative. So let's see why that is. Start with a mass at rest, some distance from a larger mass. There is energy between the two where both objects' gravitational fields interact. Now let go of the mass. It falls, picking up speed, and so its kinetic energy increases. Now this is normal positive energy. The rock would hurt you if it fell on your head. But, and here's the important part, since the system is isolated, the total energy hasn't changed. So if the kinetic energy gets more positive, the gravitational energy must get more negative to keep the total unchanged. Hence our formula, Ge is minus gmm over r. Well, we're now ready to make progress. Let's look at the total energy of our rock, Te. It's just the sum of the kinetic and gravitational energies, which in equation form is half mv squared minus gmm over r. Now, I hope you won't be surprised to hear the criteria that determines recollapse or eternal expansion is whether the kinetic energy is less than or greater than the gravitational energy. If it's less, the total energy is negative and the sphere recollapses. If it's greater, then the total energy is positive and the sphere expands forever. And there is, of course, a very important marginal condition. When the total energy is zero, the rock goes out, but it never quite stops and turns around, but neither does it steam ahead. So now let's look more carefully at this boundary condition between recollapse and infinite expansion. Here's the condition in equation form. The kinetic and gravitational energies are perfectly balanced. The total energy is zero. So let's just bring the gravitational term to the right. Let's cancel the little m's, bring the half across to get v squared equals 2gm over r. And then let's take the square root of both sides. Notice I've now called this v escape, the escape velocity. It's the critical speed I must launch the rock if it's not going to come back down again. This concept of an escape velocity is very important in astronomy. For example, if we're standing on the Earth, so r is 4,000 miles, and the mass, m, is the Earth's mass, then the escape velocity is about 11 kilometers per second. That's 10 times faster than a rifle bullet. That's why the old adage, what goes up must come down, is effectively true, because no one can throw or even shoot anything that fast. But if they could, and if the air wasn't there, then it wouldn't come down. It would escape and just keep on going. Now, for our cosmological purposes, there's actually a more interesting way to express this critical condition. So let's look at that now. Here's our initial situation. You can think of it as today's universe, and I'm going to use a subscript 0 for any property of this initial situation. So the sphere has radius r0, with rocks moving out with a Hubble law. So the outermost rock has outward velocity v0, which equals h0 times r0, where h0 is a Hubble constant that defines the initial velocity pattern. Also, since density is simply mass over volume, we have an expression for the total mass, m0, of the rocks. It's just volume times density. That's 4/3 pi r0 cubed times ρ0, where ρ0 is the average density within our sphere. So back to our equation for zero total energy. Let's insert our expressions for v0 and m0, and nicely the little m's and the big r0s all cancel, and we're left with a rather simple expression. If the ratio of the Hubble constant squared to the sphere's density is equal to this number, 8 pi g/3, then the expansion is on the knife edge between eventual recollapse and infinite expansion. One last manipulation. Let's just rearrange this as a condition for the density, ρ0 crit equals 3h0 squared over 8 pi g, where this is called the critical density. For a given Hubble constant, ρ0 crit specifies that density that is just able to halt the expansion. Notice that this critical density plays just the same role as the escape velocity. So a universe that has a density equal to the critical density is expanding at the escape speed. Now, at this point, you should be feeling a bit of déjà vu, because we met both these equations last lecture, where they gave the condition for a flat Euclidean geometry. This is extremely interesting. A Newtonian analysis of the universe's expansion seems to resemble an Einsteinian analysis of its geometry. If the universe's geometry is closed, its expansion will recollapse, whereas if the universe's geometry is open, it will expand forever. This is a wonderful equivalence between dynamics and spatial curvature. Now, I do need to warn you that this is only true for a universe containing just matter. As we'll see next lecture, if the universe also contains dark energy, then this correspondence between geometry and future expansion will no longer apply. Okay, let's return to the sphere of rocks and see if we can figure out its full expansion history. Our approach is pretty straightforward. As the rocks move out, they slow down. Their kinetic energy is decreasing as it gets put into the gravitational energy, which is increasing. The crucial thing to remember is that the sum of these two energies, the total energy, is fixed throughout the whole trajectory. It may be positive or it may be negative, but either way, it's fixed. This is, of course, an example of a deep principle of physics, the conservation of energy. So let's rotate this diagram over and make expansion size our x-axis. Now let's make the y-axis energy. with zero in the middle, so positive energy is above and negative energy is below. I'm going to show you a number of graphs of this kind, and they really help to see what's going on. So here's the diagram for a critically expanding universe. The gravitational energy is in blue. It increases towards zero as the rock moves out. Now remember that for a critical universe, the total energy must always be zero. So that's given by the red line. But the kinetic energy, when added to the gravitational energy, must equal this red line. So the kinetic energy must follow this yellow line. It's just the mirror of the gravitational energy. At every distance, the blue line plus the yellow line equals the red line. As you'd expect, the kinetic energy, the yellow line, drops as the rock gets higher and slows down. Now, so far so good. But now we need to go from these energy curves to the size history curve, S of t. Now, the first step is actually easy. Since kinetic energy is a half mv squared, then taking its square root gives the rock's velocity. Now, that's the purple dashed line. It drops just as you'd expect. Now, the second step uses this purple curve, which tells us how fast the rock moves to the right, and a little bit of math I don't have time for, to get to these two curves. Notice the x-axis is now time. The purple line goes with the right-hand y-axis and shows the rock's velocity. It drops as time passes, as you'd expect. The green line goes with the left-hand y-axis and shows the rock's size. It increases as time passes, again, just as you'd expect. These are the curves we're after. They show the sphere's size and expansion speed over time. It's the expansion history. And they are, of course, closely linked. When the velocity is high, the green line is steep. When the velocity is low, the green line is shallow. Notice that our analysis shows the size going to zero with an initially infinite expansion speed. That, of course, is the Big Bang. Whatever launched the Big Bang needed to provide an enormous expansion speed to liberate everything from an incredibly compact and tightly bound region. Now, we'll return to this extraordinary launching situation in lectures 30 and 31 when we look at inflation's amazing launching mechanism for the expansion. Okay, now let's look at a universe that has positive total energy, so it will expand forever. Here's the gravitational energy in blue, just as before, but now the total energy is up here in red. So the kinetic energy must be this yellow line. It's exactly the same shape as the previous case, but shifted up. Taking its square root gives us the expansion speed, which converges to a constant value. Here are the graphs against time. After a little bit of deceleration, the size continues to increase at a constant rate as the velocity settles on its final value. After the universe got its launch, it just coasts, with too little gravitational force to slow it down. Our final example is when the total energy is negative, so we're expecting it to recollapse. In this case, the total energy, the red line, is now below the x-axis. So this time, the kinetic energy drops, but it hits zero. But at zero kinetic energy, the rocks are stationary. You can't go below zero to negative kinetic energy. It doesn't exist. So at this point, the expansion turns around and collapses back in, retracing the outgoing trajectory. Over on our time graph, you can see the velocity dropping to zero just when the scale factor reaches its maximum. Then, past turnaround, the universe falls back symmetrically, and we have a big crunch that mirrors the Big Bang. In that final collapse, all the matter rains down, accelerating as the gravity gets stronger and stronger. The final incoming speed rockets off up to infinity. This figure now shows all three models together. It's just like throwing three balls up in the air with slightly different speeds. They start out together but gradually separate. The one below the escape speed eventually turns round, while the others just keep on going. Now, our approach so far has been mainly graphical, but I'd like to very briefly recast this in equation form. Please don't worry if you don't follow this completely. My main reason for doing it is to compare in a moment our Newtonian toy model with the real thing, the Einsteinian full universe. So here we go. We start with this equation for the outermost rock's total energy, the sum of its kinetic and gravitational energies. But now, since the total energy is constant, then the sum today on the left with subscript naught equals the sum at any later time on the right with no subscript. Notice right off the bat we can cancel all the little m's. The outermost rock's mass isn't relevant. Now, above this equation are several small equations, all of which we've met before. Briefly, the sphere's mass is its volume times its density, the rock's initial velocity is the Hubble constant times the initial radius, we have the formula for the critical density, and the formula for the scale factor. So at this point, we just dust off our high school algebra and plug all these little equations into the big one and tinker for a while until we come up with this new equation. Now, I'm going to postpone looking at this equation in detail until next lecture, so for now just notice two things. First, there are three terms, two on the left and one on the right, corresponding to our original terms for kinetic and gravitational and total energy, though here they're expressed a little differently as ratios. Second, the solution to this equation gives us the expansion history, S of t, and there are two things that are going to affect it. The first we've already met. It's the ratio of the initial density to the critical density, rho naught over rho naught crit. But the other thing is how the density of the sphere, rho, changes with its size. For our rocks, the density drops as the sphere expands. But next lecture, we'll discover that the density of dark energy doesn't drop with expansion. And it's because of that that it drives an accelerating expansion. Okay, time to make a shift now from our Newtonian analysis to one which uses Einstein's theory of gravity, general relativity. Unlike Newton's simple inverse square law for the gravitational force, Einstein's formulation of gravity is much more subtle and challenging to understand, and all I'm going to do is just sort of show it to you. This is, in fact, his second most famous equation, the first being, of course, E equals mc squared. Here it is. It's called Einstein's field equations, and it reads Gij equals 8 pi g over c to the fourth times t ij. Notice I said equations, plural. That's because the subscripts, I and j, both stand for one of the four space-time coordinates, x, y, and z for space, and t for time. So in fact, there are 16 equations here masquerading as one. Now the left-hand side, Gij, specifies the space-time curvature, while the right-hand side, Tij, specifies the distribution of mass and energy within the space. Normally, these equations are extremely difficult to solve, but the cosmological application has one enormous advantage. The matter and energy are distributed uniformly throughout all of space. This symmetry reduces the 16 equations to just two, and in fact, we really only need one. The first person to find the solution to Einstein's field equations for a homogeneous universe was the Russian cosmologist Alexander Friedmann in 1922, and so we now refer to the Friedmann equation. Here it is. We don't need to look at it in detail, but notice it has a familiar form. It has three terms, and the two on the left look like things we've encountered in our Newtonian analysis. The first is the rate of change of the scale factor, squared, and the second includes the cosmic density and the scale factor. It's the right-hand term that looks new. It describes the geometry of the space. Curly r is the space's radius of curvature, while k keeps track of whether the curvature is negative, 0, or positive, by being -1, 0, or +1. So, what was our total energy in the Newtonian treatment becomes a geometry term in our Einsteinian treatment. But in fact, the similarity is much greater than you might think. If we make some simple substitutions just like we did before, with a few equations that we already know, so we're not adding anything new, then this is the equation you arrive at. Does it look familiar? You bet. It is identical to our Newtonian equation for an expanding sphere of rocks. Now you know why I spent so much time analysing that sphere of rocks. In the particular case of a homogeneous universe, the Newtonian analysis turns out to yield exactly the same result as the vastly more sophisticated theory of general relativity. The first people to fully appreciate this and begin to frame cosmological models in Newtonian terms, which are much more intuitively understandable, were the British and Irish cosmologists Arthur Milne and Bill McRae in 1934, although the roots of this work go back to the American mathematician George Birkhoff. See, in 1923, Birkhoff managed to show that inside general relativity, if you can draw a sphere and outside that sphere matter is distributed uniformly, then the external matter has no effect on the inside of the sphere. It might just as well not be there. So, armed with Birkhoff's theorem, as it's called, we can happily carve out a sphere and analyse its motion, ignoring the much larger, possibly infinite region outside. Of course, inside our smaller sphere, we can now apply Newtonian physics, and bingo, we can recover 20th century relativistic cosmology using a 17th century theory of gravity. This is really very lucky indeed. Let me quickly summarise this lecture and set the stage for the next one. Our goal was to understand how the universe's expansion might evolve over time. As is often the case in physics, we set up a toy model to see what might happen. A sphere of rocks moving radially outward, obeying a Hubble law. Although we can intuit how the rocks respond to the force of gravity, we actually chose to look at the energy of the rocks instead, which includes both their kinetic energy and their gravitational energy. Now, since energy is always conserved, the sum of these remains fixed. And as the rocks climb higher, to higher gravitational energies, their kinetic energy drops, so they slow down. We recognise two situations, one in which the rocks went out forever, and another in which the rocks went out but recollapsed. Which occurs depends on whether the kinetic energy is greater or less than the gravitational energy. The intermediate case, in which these energies are equal, occurs if the rocks move exactly at the escape velocity, or equivalently, if the sphere has the critical density. We looked at the expansion histories of these three kinds of universes, making use of graphs of the various energies. We then compared our Newtonian analysis with a proper Einsteinian analysis and found that the universe's isotropy and uniformity enormously simplifies things, and the result can be expressed by the relatively simple Friedmann equation. Amazingly, after a little bit of rearranging, this equation is identical to the Newtonian result. So our simple analysis of a rock sphere turns out to be valid for the real universe. Now, we've done well, and this has been a challenging lecture, but we now have all that we need in order to bring in the other major components of the universe, radiation and dark energy. Explaining just why dark energy seems to give the universe a push and accelerate its expansion will be our primary aim for the next lecture. So stay tuned.